All right, welcome to Map Divulged. So this is our introductory class for coordinate bashing, and this is week 11. So I'm your teacher, Naveen Mukat. So I've been doing math for quite a while, and our TA is Will. Will, would you like to introduce yourself?
Yeah, hey guys, I'm Will. I'm a senior at the Texas Academy of Math and Science in Dallas. And just a quick reminder for today, if you guys have questions or answers or anything, please direct them to me through DM, as Naveen will not be able to look at his messages. Yeah, that's about it.
All right, thanks for that, Will. We're gonna start. So what coordinate bashing, you guys might have heard this before. It's not a technique that I would recommend all the time because, as the name implies, it's very bashy. So if you don't know what bashy means, it means very computation heavy, very time consuming. But a nice way we can describe it, suppose we had a triangle. Whoops. Like so. And let's just say, for the sake, just for hypotheticals, that this side length is 13, this is 14, and this is 15. Now let's just say we want to find like the centroid of this triangle. Just say that's right about here. Well, you can use like normal geometry, like where you try to use like triangles and stuff. But coordinate bashing, what it does, it takes these geometrical figures and puts them on a Cartesian plane. So we're going to assign like ordered pairs and equations of lines to the triangle itself. For example, we can assign this point as the origin. So we're basically placing it on a plane, an XY plane that looks like this. So that's our plane. And let me just write X and Y. And we put this point, we'll call it A, at the origin. And let's call this point B, this point C. What coordinate bashing allows us to do is basically determine this point, the centroid, which we typically call point G, by setting it up to be an intersection of two lines. So let's see how we'll do that. If you guys have worked with 13, 14, 15 triangles before, a very key insight of them is that you can split it right down this altitude right here. Like so. And on the left-hand side, you'll get a 5, 12, 13 triangle. And on the right side, you will get a 9, 12, 15 triangle. So now we can assign coordinates to A, B, and C. We already know A, it's at the origin. But now we can know B, which is 14, 0. And now we know point C, and this is 5, 12. Because we have 5 over here and 12 over here. So what is our centroid? Our centroid is the intersection of medians. Well, what are medians? They're segments that go from a vertex to the midpoint of another line segment of a triangle. We can choose medians that allow us to do math really easily. Now, what's the easiest midpoint of a side to find here? Well, clearly it's AB. It's on the x-axis. The midpoint's really easy to find. So we're going to say, let's pick a different color. Let's choose orange. The midpoint's right here. Oh, that's not a color. It's right here. And it's between 0, 0 and 14, 0. So this will be 7, 0. Now we can draw a line. This is going to be quite a rough line. Let's make it nice. And we'll draw, where'd that go? All right, that scared me. I really thought everything had been undone. This line, no wonder I'm on an eraser tool. And we know that this intersects at a point here. And we know that point is 7, 0. Now we have 2 points. We can define the line with algebra. We can define this through an actual expression. So if it goes through 5, 12 and 7, 0, we can say that y is equal to, what color should we use here? Let's just use white again. Y is equal to, the slope is -6 because it drops 12 and goes across by 2. So it's -6x, and it's going to be plus 42. You can find this by plugging in any point here. You can plug in 5, 12, or you can plug in 7, 0. You'll get y equals -6x plus 42. So we know that the centroid lies on that line. Let's find another one. The next median is a little bit hard to find, but we can make stuff easier by choosing this median right here. Why is that? Well, this median goes through the origin. So the equation for a line is a lot simpler to find. So what's this mystery point over here? It's the midpoint of BC. So it's between 5, 12 and 14, 0. And this will have coordinates 19 over 2 and 6. The equation of this line, since we know the other point it passes through is 0, 0, has to be in the form y equals mx. There's no plus b term since it goes through the origin. And doing algebra, plugging in 19 over 2 and 6, we find that m is going to equal 12 over 19. So what do we know? We know that our centroid, point G, has to be on the intersection of these 2 points. So let's move those equations over here and we can solve this. We set them equal to each other, and from there, we just do normal algebra. -6x plus 42 is equal to 12 over 19x. Multiply everything by 19 to make our lives easier. Well, relatively easier. We get -126x is equal to -42 times 19. This cancels, and we get that x is equal to 19 over 3. So we know that the x coordinate of the centroid is 19 over 3. And to find the y coordinate, well, it has to be on one of these lines. We can plug this straight into this equation over here. So 19 over 3 times 12 over 19 is going to equal 4. So this is a pretty good example of how coordinate bashing works. You just take a geometrical figure, place it on the xy plane, find, and most common trick you're going to use is the intersection of 2 lines. That's probably the recurring theme of coordinate geometry. Let's find another one. What's a good example? We're back to circles. Suppose we had the circle, and we call it circle O. And let's label that point O. And we're going to have point B right here that lies on the circle. And we have this point P such that PO is perpendicular to OB. Now, the reason I'm drawing this out instead of preparing it beforehand is because, like I said last time I taught a class, drawing geometry problems is one of the harder parts and one of the most crucial parts of geometry. So if you guys are taking an AME or an AMC, if you can bring colored pencils, they can help you highlight certain things a lot easier. You can see me using a lot of colors in this. So PO is perpendicular to OB, and another thing is that PO is equal to the length of the diameter. So you can say that PO is twice the length of OB. How can we mark that? We can mark it like this. And we're going to draw PB. And you'll notice it intersects the circle at another point. And this is point A. So the question is, what is PA over AB? If you're wondering what the source of the question is, it's from 1999 ARML. So we want to find PA over AB. Well, we could use coordinate geometry again. So like we did last time, we're going to assign a certain point to be the origin. Now, the most natural choice here is to assign the center of the circle, point O, as the origin. So let's do that. This is 0, 0. So how do we express the other points? We don't exactly have numbers, but we can use variables. We'll assign the radius of the circle as r, like is common procedure, and we can then find that point P is 2r, 0. Point B is 0, -r. And now we have to find point A. So like you did last time, we're going to try to find some equations of lines. OP and OB, they're really easy to find, so we don't really have to worry about them too much. But PB is a tiny bit tricky. Not really, it's pretty straightforward. I lied to you. So O to -r, O, -r to 2r, 0 has a slope of 1/2. So we can express our equation as y equals x over 2. And then we can plug in 0, -r, like this. Now, point A lies at the intersection of two distinct geometrical figures. It lies at the intersection of a line and a circle. So we also have to know the equation of a circle. Well, this is pretty straightforward as well. X squared plus y squared equals r squared. How do we find the intersection of these two? We had to set them equal somehow, right? It is just a tiny bit complicated, and it's very bashy. It's very easy to mess up, which is why I wouldn't recommend coordinate bashing. It's easily one of the quickest ways to make a silly mistake, but sometimes it's just a little bit, it's too useful to not do. So we're going to substitute this value for y into this y. So let's do that. What color should they use here? Let's use light red or orange, I guess. So 1/2 x minus r squared plus x squared equals r squared. Now, if you've done this before, you might notice that the r squared actually cancels out. So let's see how it does that. Expand the entire thing, x squared over 4 minus rx plus r squared plus x squared equals r squared. So r squareds drop out. And now we are left with 5x squared over 4 is equal to xr. Now you gotta be careful here. Your first instinct might be to cancel out the x, but you have to think, could x be 0? Well, very clearly x is not 0. You can tell that a does not lie on the y-axis, so we can go ahead and cancel as normal. But please watch out for this, because this may not always be the case. So r is equal to 5x over 4. We can plug that equation into y. So over here, we say 5x over 4. So we get that y is equal to negative 3x over 5. A better idea, actually, I just thought about this. A better idea would be to take the equation for x and plug it in. So we can express this as r is equal to, as x is equal to 4r over 5. And this will give us coordinates all in terms of r. So we can plug this in instead. So this will give us 2r over 5 minus r. So y is equal to negative 3r over 5. So this means that point A lies on the coordinate 4r over 5, negative 3r over 5. And we want to find PA over AB. And this is pretty straightforward. We have 0 to 4r over 5 to 2r. And this corresponds to B, A, and P. PA is 2r minus 4r over 5, which is 6r over 5. And 4 over 5 minus 0 is 4r over 5. So the answer is 6r over 5 to 4r over 5, which is 3/2. Or 3/2 if you're weird. So recap of the strategies that we used here. Assign the point to the origin. Find the equations of lines. Express your missing points as the intersections of two geometric shapes. This is going to be quite a short lecture, actually. Coordinate patching doesn't really have too much information on it. But we can pull up a lot of sample problems. This one's from math counts. This thing does not want me to draw a 45-degree. There you go. And what's the problem here? We're going to say that this is triangle ABC, where C is a right angle. And we're going to say that point M is the midpoint of AB. Point N is the midpoint of AC. And if you have questions, M and N are parallel. MN is parallel to BC because they're both midpoints, those are similar triangles. And point O is the midpoint of AM. So the perimeter of ABC is 112. So A plus B plus C is equal to 112. And ON is equal to 12.5. Want to find the area of MNCB. So let's draw some line segments to make sure that we know what we're talking about here. And we'll draw this. So your first use is probably similar triangles, right? You can definitely use similar triangles pretty easily. However, this is a coordinate bashing lecture, so we're going to use coordinate bashing even though it might not be the most optimal choice. So like we did before, assign that point to the origin. So 0, 0, perfect place for the right triangle. We're going to use the right triangle place again. So what do we call everything else? Well, we're going to do something kind of interesting. Instead of calling this something like 0b, we're going to call this 04b. Why are we doing this? Well, we have a bunch of midpoints. We know we have this over here, we have this over here, and these all are going to have, this is going to have a length of b, this is going to have a length of b, this is going to have a length of 2b. So the math is easier when you avoid fractions, right? Your brain doesn't exactly like fractions, it likes nice round numbers a lot better. So we're going to call it 4b. And I just realized this is flipped, this should be 4b0. That's a very interesting mistake to make. We're going to do the same thing to point A. We're going to call this 04A. How can we describe every other point? Point M is the midpoint of A and B. Shouldn't take too long. Point O is the midpoint of A and M. Just average out the coordinates. You do the same thing for point N. And we're there. So now what? Well, what information have we not used from the problem? We still haven't used the fact that A plus B plus C is 112, or ON is equal to 12.5. Let's use ON equals 12.5 because we do have a line to describe that. We're saying that the distance between point 0, 2A and the distance between point A, 3B is 12.5. Here we can use the distance formula. And the distance formula is just the Pythagorean theorem with extra steps. So the distance between N and O on the x-axis is A. This is between O and N on the y-axis is going to be 3b minus 2a. And that's a right angle. Therefore, our distance hold on, did I switch up things? Yep, I think I did. I held over the stuff from last time, which makes a lot more sense now that I think about it. There we go. Will, if you notice these things, let me know, please. I think people are messaging me about this. Yep. The program I'm using is Penbook. So yeah, that's a brain fart. I think that's another common silly mistake with coordinates is just flipping the coordinates around. I know I did it a lot back when I did math counts. I still do it now, as you just saw. So this is a lot easier now. The distance between n and o on the x-axis is b. The distance between n and o on the y-axis is a. So the distance between them will be square root of a squared plus b squared. And we know this is equal to 12.5. So now the other problem, the other piece of information that we haven't used is a plus b plus c equals 112. Let's find out that now. We know that AC is equal to 4a. So this thing right here is equal to 4a. BC is equal to 4b. And AB, the same way we did it before, on the x-axis is 4b, on the y-axis is 4a. So distance formula tells us that this thing has to be, well, I don't have space to write it, but 4a squared plus 4b squared. We know the value of that. That's just 4 times the original one, which is equal to 50. Let's move everything because this is getting cluttered. That's another thing I should note. When you're doing bashing of any type, things tend to get cluttered. Please keep your space organized because you'll avoid silly mistakes like that. I think that was like one of our first lectures that we did actually. So you know that ABC, A plus B plus C is 112. Let's copy that over. So A plus B plus C, we know what AB is, which is 50, as we just saw. We know what A and B are. They are 4A and 4B. So 4A plus 4B plus 50 is equal to 112. So this implies that 4A plus 4B equals 62. So therefore, A plus B is equal to 31 over 2. When you coordinate bashing, don't lose sight of the original question. What is the area of MNCB? We want to find the area of this trapezoid right here. So how does this help us in any way, shape, or form? Well, we're going to drop a line from M to BC such that this line is perpendicular to BC. How does this help us? Well, it breaks our trapezoid into 2 parts. We have, well, let's label this point first. This is point M prime, and we'll call this trapezoid. This trapezoid is this rectangle plus this triangle. So now we can use area formulas to figure out everything here. And you can just think, and hold on. The side length of this rectangle, it's 2a over here, 2b over here, so this is equal to 4ab. It's 2b over here, 2a over here, this is equal to 2ab. So the area we're looking for is equal to 6ab. So now we have to find 6ab. I told you this is going to be bashy, so here we are. If you remember the algebraic manipulations class that we did, you might recognize some of this. We know what the square root of a squared plus b squared is, and we also know what a plus b is. If we square this original, whoops, that's highlighted a little bit more than it should. If we square this part, let's do that right now. Let's convert it to fractions so we don't deal with decimals and the math is a little weird. So 25 over 2, squaring this gives us a squared plus b squared is equal to 625 over 4. And squaring this expression right here, a plus b equals 31 over 2, gives us that a squared plus 2ab plus b squared is equal to 961 over 4. Well, now you should know what to do. Subtract these two equations. You get 2ab is equal to 961 over 4 minus 625 over 4, which is equal to 336 over 4, which is equal to 84. And I want to find 6ab, so we multiply this by 3. So 84 times 3 is equal to 252. And that's our answer. This is coordinate bashing. It's not the most enjoyable thing in the world, but it gets the job done. I had a phase back in 6th grade where I would coordinate bash every single geometry problem. And yeah, it works. It's very time consuming. And in contests like math counts and AMC, time is pretty essential. So as you do a lot of geometry problems, you should get an intuition on when coordinate bashing is applicable and when it'll be reasonably quick. So at this point, we beg the question, when should a coordinate bash, right? I want something more than just figure it out by yourself. Well, I guess I can provide a bit of a checklist for you, just like a bunch of signs that coordinate bashing might be right. So, checklist. So first thing, are there right triangles? We've seen right triangles a lot. Just look at the last couple of problems that we did. We had right triangle right here. We had a right triangle right here. Let me just highlight that. We didn't exactly have a right triangle over here. We did have something else that is on the problem, that on the checklist. But the right triangles have appeared in 2 out of our 3 examples so far. So that's a dead giveaway. And the reason right triangles are a good candidate for coordinate bashing is because they can provide us with the distance formula, which is something that you use a lot in coordinate bashing. And we just used it here to find a squared plus b squared. And we could actually use this here if we wanted to find the actual length of PB or the actual length of PA. We can use a distance formula there. That's why right triangles are so nice. Another thing is that if there is a point of origin, where you can assign a point that makes the math a lot easier if you make it the origin. For this problem, for right triangles, it's typically the right angle, which is another reason why right triangles are so nice. For this problem, same thing. It was the vertex of the right angle. For this problem, it was one of the vertices of the triangle that allowed point B to lie strictly on the y-axis. The x-axis, yikes. Yeah, so whenever there's a good point of origin, coordinate bashing might be the right choice. Another thing is if you're looking for a ratio of distances. In our circle example, we had PA over AB. Now, normally with ratio of distances, similarity should get you pretty far, but coordinate bashing can also be another tool you can use if you get stuck on similarity. Another one is intersection points. Like if you're looking for a point, like if the entire problem hinges on the location of a point, like for example, these ones, we had a bunch of midpoints that we can use. And for this one, everything relied on where point A was on the line PB. And for this one, it's a centroid. It lies in the intersection of 3 medians. Another one is like, this is the most obvious one, right? Coordinates. If they literally tell you, we have a coordinate on 0.00, we have a coordinate on 0.512. If you have coordinates, then then use coordinates. And another one is if you have a diagram and the diagram happens to have like a flat line at the bottom, like with our 13, 14, 15 triangle. In general, when you see a 13, 14, 15 triangle, use coordinates. They'll probably be something nice. And the reason you do that is because if you align your triangle right, point B will lie on the x-axis, and you can split the triangle up into 5, 12, 13, and 9, 12, 15. You can use the same technique to find the circumcenters, the orthocenter. You can just keep going on with this. If you're really brave, and if you really want to like throw about an hour away, you can find the equation of the Euler line of this triangle purely with coordinate bashing. So you should probably try that. I'll include that as a challenge problem in the handout. Last one I just thought about, circles. When you have the intersection of two circles, or just like a bunch of, or lines intersecting circles, coordinate bashing is probably a good idea. Although when you get to circles, it can end up being especially messy. And this is because of this substitution right here, where you're substituting the value of y with what could potentially be a radical, and you get these quadratic expressions that are quite nasty to work with. But sometimes, like in this case, they cancel out, and normally you can tell when it's going to cancel when you're a bit far out. Let's do another problem. I think this will be the last problem that we do. This isn't a very long lecture since there's not much to talk about. This one is from the AMC. AMC 2004 10B. What do you know? We have a right triangle. So let's draw that out. In right triangle ACE, now let's label our points. So we're going to have AC equals 12, CE equals 16, EA is equal to 20. From that, you should determine that point C is the point of honor, the right angle. And this should be point A, and this should be point E. So the rest of the problem goes, points B, D, and F are located on AC, CE, and EA, respectively, such that AB is 3, CD is 4, and EF is equal to 5. That was a lot of words, but let's find out a way to describe that. Point B is somewhere on AC. So let's just say it's right here. Point CE is, point D is located on CE. So maybe like right here, for example. Point F is on EA. So maybe like right here. Such that AB is 3, CD is 4, and EF is 5. So clearly our diagram isn't the best. So let's redraw it. This will take a couple, and for most people this takes a couple tries when you're originally doing it on paper. If you're very lucky, you'll get it on the first try, but that requires a lot of math and just a lot of intuition. So let's draw this. Obviously, your alarm bell should be going off at the lengths being 3, 4, and 5. And here. There we go. And let's label the points as before. This is point B. Oops. Point D and point F. So the question is, what is the area of DBF? What is the ratio of the area of triangle DBF to triangle ACE? So what is the ratio of this to this? So what's your first step? Place a point on the origin. And what do we always do it as? We place it at the right angle, so 0, 0. Now let's assign the rest of the points. And let's use a different color because all this purple is getting a little bit confusing. Let's use light blue. This will be 0, 12, and this will be 16, 0. Straightforward. So now we can find the rest of the points. This shouldn't be that hard, right? Point B is 3 away from A, so this will be 0, 9. Point D is 4 away from the origin, so it's 4, 0. And F is a little bit harder to find. But one easy way you can find this, let me just make this a little bit more accurate. Let me just move that 5. We know that EF is 5 and EA is 20. So EF is 1/4 of EA. So F has to be 3/4 of the way from A to E. What's 3/4 of 16? That would be 12. So we know the X coordinate is 12. And from 12 to 0, 3/4 of the way there is 3. So there you go. F lies on point 12, 3. So ACE is a right triangle. Very easy to find, right? The area of a right triangle is, if you don't know what that is, we're in trouble. 12 times 16 over 2 is equal to 96. But what about the area of DBF? Well, we have 3 points of a triangle. And if you guys don't know what the shoelace formula is, well, shoelace theorem, it's a very, very neat way to find the area of a polygon given just its points. So let's list out the points here. B is equal to 0, 9, D is equal to 4, 0, and F is equal to 12, 3. What the shoelace theorem says is that if you list the coordinates like this, 0, 9, 4, 0, 12, 3, and then you repeat the first coordinate, so 0, 9. What you're going to do is you're going to multiply these ones, these ones, these ones, and multiply these ones, these ones, and these ones. And you're going to place at the side. So in this case, 0 times 0 is 0, 4 times 3 is 12. 12 times 9 is 108. You add this up to get 120. 9 times 4 is 36. Go back to my other color. 36. 0 times 12 is 0. 3 times 0 is 0. This will be 36. You probably notice why it's called the shoelace theorem, because it looks like a pair of laced up shoes. So what we're going to do is we're going to subtract these numbers. So 36 minus 120. And we're going to take the absolute value of this and divide it by 2. This is going to be 84 over 2, which is 42. So the area is 42. We're not done yet, though. I boxed this in, but that doesn't mean that's the answer. We're looking for the ratio of area of BDF to area of ACE. So 42 over 96 is equal to 7 over 16. So that's our answer, 7 over 16. So just to recap the shoelace theorem, it's very useful, especially for coordinate geometry. We list our coordinates vertically and repeat the first coordinate. Make sure you do that. And you multiply them diagonally, tally them up on each side, subtract them, find the absolute value, and divide by 2. I can't tell you how many times I've seen people miss these problems because they forget to divide by 2. Divide by 2. So once you do that, we got 120 minus 36 over 2, which is 42. And then we know the area of the triangle, which is 96. So our answer is 7 over 16. I think we can do one more problem. So this is one from, I think it's from the same test. Yeah, it's from AMC 2004 10B again. We have a triangle, a right triangle. At this point, you shouldn't be that surprised. And it's a 5, 12, 13 triangle. That's hopefully accurate. Overshot it. There you go. And let me just make this a brighter color. So all triangles have an inscribed and circumscribed circle. And we want to find the distance between the center of those circles. So the inscribed circle looks something like this. A very good circle, by the way. And the circumscribed one looks something like this. We want to find the distance between these. Keep in mind that the center of a circumscribed circle on a right triangle is at the midpoint of the hypotenuse. So let's make it a little bit neater. Just take out the circles completely. We have this, and we have something like this. So we do the same thing we do all the time. Put a point at the origin, and we'll say that this one is 0.00. Different color, please. And we say this one is side length of 5, so this is 0, 5. This is 12, 0, and the midpoint between 0, 5 and 12, 0, this is going to be 6, 5 over 2. So we already found the center of the circumscribed circle, not too hard. But now what? Well, something that is very useful is this formula concerning inscribed circles. A is equal to RS. What does this mean? The area of the triangle is equal to the radius of the incircle times the semiperimeter. The reason why this is true, let me just sketch out the circle again. That looks deformed. There you go. That's marginally improved. So why is this formula true? When you draw the incircle, if you draw the tangent points, like where the circle touches the triangle, these are right angles. And let's draw some other lines over here. That will make this a little bit more clear. What do you see here? We have a bunch of right triangles where the heights are R and the base is the length of the triangle. If you add all these up, you know that all the heights are going to be R and all the lengths are going to add up to the perimeter. And since it's the area of a triangle is base times height over 2, it's the radius times the perimeter over 2, which is the radius times the semiperimeter. So that's where this comes from. How does that help us? We can find the radius of the circle. Because we know the area, it's 5 times 12 over 2, which is 30. We can find that semiperimeter pretty easily. It's 5 plus 12 plus 13 over 2, which is 30 over 2, which is 15. So 30 equals 15R. So R equals 2. Now what? Let's go back to the diagram. The semicircle, the incircle is tangent to the side of the triangle, and it forms a perpendicular. So if this line is horizontal, then this line is vertical. If this line is vertical, this line is horizontal. If the radius is 2, then this is also 2. This is also 2. This is also 2. Therefore, this point, the incenter, is on point 2, 2. We can use distance formula. So square root of 6 minus 2 squared plus 5 over 2 minus 2 squared is equal to square root 16 plus 1 over 4, which is equal to root 65 over 2. And there's your answer. So that concludes our meeting of Math Divulged. It's now 4 o'clock. So you're free to leave. Thanks for coming to this meeting. I know it's a bit on the short side, but this is a pretty short lecture by design. So if you have any questions, feel free to ask. I'll be in chat, so will Will. Will, that's your noise, right?